Let's get going. And this will be very informal for various reasons. I like informal. I like lots of questions. And also because I put it together informally. Yeah, I was running around the place trying to interview candidates just this very morning. So there are things that are going to be in odd places, but together we'll put it together. And I also have no idea what level we should be at. Okay, because parallel computing is the Wild West at the moment. It is the most fun you can have. It's really, really important, and yet because there's no dominant technology, there's lots of them. And there's lots and lots of different hardware configurations and so forth. We're going to talk mostly about R, and then yesterday I started doing a whole lot of stuff that wasn't in R, because we don't need R, because you can still be using R, but there's lots of different ways, and all pretty basic stuff. I believe I've pushed material here, so the github.com DSI Davis, and then there's a parallel R. So there's these slides, which are, again, more for reminders to me as to what we're supposed to be talking about, as opposed to comprehensive facilities to get things going. I say lots of questions. Please ask lots and lots of questions. What are we trying to do here? This is easy. In my mind, there's only one reason we care about parallel computing. It's speed. End of story. Yes, we've only got one goal. Okay. There's lots of ways to get speed. We did a workshop on writing efficient R code, and there's ways to do that. This is totally orthogonal to that, ideally. If you're lucky, this is totally orthogonal. The faster you make your code by writing good R code, by writing C code or whatever it is, that's not quite true. But the more you refine your code that runs serially, the faster it will run in parallel. Okay, as long as you're not changing the whole computational model. So they go well together. If you're very, very lucky, and the trouble is most people aren't, you actually, well, that's not quite true. In many cases, you are very lucky. In other cases, it's hideously hard. But some computing is trivially parallel. Okay, we'll talk about that. Okay, but some of it can be just brain dead easy. Computer scientists think parallel computing is really hard because they tend to deal with much more complicated problems than statisticians and data analysts. Data analysts tend to deal with problems that go, I wonder how I could run these two things that are completely separate in parallel. Oh, look, they don't interact with each other. Yes, and that's what we're going to talk about a little bit about today, mostly today. Okay, but basically here are the approaches. You can explicitly dispatch code to do tasks in parallel. That's kind of where we're going to take. We're going to actually run. We're going to do things directly ourselves, and then you need to actually know how to write parallel code. It's super high level in R, okay? By design, it doesn't give you full control, but it gives you a lot of stuff. However, there are some simpler ways, and my philosophy is always go for the simpler way first. Many of you will be doing linear algebra, whether you like it, know it, or not. Okay, you'll be fitting linear models, and you'll be doing QR decompositions and so forth. You'll be doing matrix multiplications, but you know it or not. Okay, hopefully you don't know. Hopefully the functions are super high level, that you're going off and you're doing some wacky stuff in Markov chain Monte Carlo, and lo and behold, in some C++ code that's in a package somewhere else, there's somebody doing some matrix algebra to do transformations of matrices. You can win really, really easily on that front by actually running your code in parallel without changing anything during your R session. Okay, and this just generally works, and there's some fun stuff people talk about. But basically, who knows what BLAS is? 2 or 3. So it stands for a basic linear algebra subprograms, subroutines system. Okay. Pick your S, okay? But basically, it's a collection. It's a C++, it's a compiled library of routines, okay? Of mathematical linear algebra routines for dealing with linear algebra, as the name suggests. There are people, I kid you not, who spent their entire career figuring out the algorithms and implementing variations of these linear algebra systems. This is what's called a reference library. It has an implementation that's available everywhere, okay? And then there are better versions, okay, that have really smart, clever things implemented in them that are specialized to particular chips. Intel provides its own version of glass to work best on its chips. Okay, and then there's another thing called Atlas, which is the auto tuning library. Many years ago, when we would install it, you'd install it from source on your laptop, on your computer. It would take about 6 hours to install, because it would actually go off and figure out what was the best setup for your computer. Okay, it would actually benchmark a whole load of algorithms and say, this is the best for you for this task, this is the best configuration. So as a result, it was highly optimized. So there are different versions of this. Microsoft, for example, Microsoft advertises that they have a very fast version of R. Essentially, what it is R with the Intel version of Glass installed. Okay, so we can't, the R community can't actually distribute it for licensing reasons, but you can download it for free. Okay, you can download various different versions of Glass, and you just install it, okay? And then R will pick it up. Sometimes you have to tell R to pick it up, and you have to specify an environment variable or put it in the right place. But basically, you can hot swap a Glass implementation into your R configuration, and it will just pick it up. And what is important about most of the modern Glass implementations is that they actually use multiple cores, multiple CPUs on your single machine. They will actually look and see how many CPUs you have, how many cores on each CPU, and it will then choose, or you can tell it how many cores to use for a particular task. And you are now doing parallel computing, and what have you done? You've installed Glass. That's it, okay? Nobody should be using R without installing Glass, an alternative to Glass, a fast version of Glass. If you're on an AMD chip, there's an AMD library. If you're on an Intel chip, there's an Intel library. There's also Atlas, there's GoGlass, and all sorts of different things. I wish it was simple. I wish there was one. Okay. The whole point of today is there isn't one. There's not one Glass, and there's not one approach to parallel computing. It's the Wild West. Okay, so do this. Okay, and if you have any difficulty, you ask questions. It's all Googleable. You know, it's annoying. It's system level stuff. You can, by the way, how many of you have ever installed R from source, from C code, and actually compiled R? Okay, not many. It's really, really easy. I might even actually do it live to show you how you can make it go faster. But the point is, when you're installing R, you can actually say, here, use this Glass. It's very, very simple. But you can also do it retroactively after using someone else's R. And that's the other thing is, if you install your own version of R, you also get to control all the configuration options, so you can make it go faster. Okay, so there's good things to be had, and I'm not suggesting you should be doing that, but it's a nice skill to have, and it really is not hard. If you're going to make code faster, again, speed is the issue. We go back into what we talked about in making our code efficient. You use the profiler, you find out which bits are actually taking the most amount of time. You then start thinking hard, okay, about how to rewrite that in R in a more effective way. Sometimes you actually can do this and you get speed up. In other cases, you actually basically go, oh dear, I'm going to actually have to change the algorithm. That's the last resort. Okay, you can write C and C++ code. I want you to stay away from this. Why? Because for the most part, you're not going to get parallels. You're going to have to write the parallels in the C++ code. There are some supporting libraries, but it's hard. It is stupidly hard. Okay, so that in this case, you're much better off in R because in C++, you're either going to have to use a thing called OpenMP or MPI to actually talk to other machines, or you're going to be stuck on a single machine with multiple cores. Okay, and if you want to do both, you can, but you're going to have to learn a whole other sort of language in addition to C. Okay, and that an extra sort of set of primitives. And it's somewhat constraining. Something that Clark here is working on is actually, let's take your R code, we'll parallelize it for you, and we'll make use of all the different machines, all the different GPUs, and so forth. So ideally, you stay in R. I think everyone here wants to stay in R. Okay, and if you don't, that means you haven't written any C++ code. When you do, and you want to go back to R. Okay, it's just not fun. Okay, so hopefully we can have, the ideal is that you just change the name to one function. And we can actually do this. You change the name of the lapply function to MC lapply, we're done. And you will actually get access to parallel computing. passively. Okay, that's basically it. So, but I just want to make sure that you study. These are important things to do, and when you really need speed, we're going to go after this as well, but they're slightly orthogonal. But this thing is just do it. Just install a new version of BLAST because you get the parallelism in the linear algebra stuff. If it turns out you're never using linear algebra, well, you get no benefit, but you're not hurt in any way except for the 10 minutes it took you to do this. Okay? So, what can we do in parallel? Some things we can't do in parallel. When I'm waiting, when the input of one task needs the output of another task, I have to wait. I cannot do stuff in parallel. That's pretty obvious. Parallel computing is really, really simple and obvious, and it's extraordinarily hard. Okay? It's kind of fun. It's 2017. It's 20 years since I did my thesis. It was on parallel computing in the S language. Okay? And we've come a long way and not so much in certain ways. But the big thing is it's actually easier as long as you're staying high above things. We have this term. How many of you have seen this term before? Embarrassingly parallel. Lovely term. It's not in any way embarrassing. It's just wonderfully parallel. It's joy of joy. No thought whatsoever. Just merely means we look. We can't claim any credit for doing this. But embarrassingly parallel tasks are when this task does not depend on this task, and it doesn't matter which order I do them in, or if I do them at the same time. An enormous number of tasks in data analysis can be done that way, okay? Or at least broken down into tasks that can be done in parallel, and then everybody must come together at the end when all of them are done, and then we move on again. So the obvious example is this, is sort of when you actually have simulations, when you're doing a simulation, you actually have to change the parameters. They're all independent. If they're not independent, that's bad news. Then they're not. Then the order matters, and they're not actually simulations. So the obvious thing to do is you just get a collection of parameters, and then you send a job off with one set of parameters. Then immediately come back and send another job off with this different set of parameters, and keep going. And you just do this a million times. And now, if they're all running in parallel, if you do 100 of them, you'll be done by the time it takes the longest to finish. Okay, so if they all take 5 minutes, you're done in 5 minutes, even though it would take 500 minutes if you did them serially. This is all obvious stuff. Okay, resampling is another one we do. Bootstrapping, okay, a permutation test. If you're bootstrapping, who doesn't know what the statistical concept of a bootstrap is? Okay, so a bootstrap is just the idea of pulling yourself up by the bootstrap, where you're actually, instead of using asymptotic estimators and formulas for estimators, we're actually going to resample our data with replacements. We're going to get a new data set, which will be a subset of our original one, but kind of all mixed up, okay? And then we're going to actually fit the model again, and then we do this over and over and over and over and over and over and over again, and then we look at the distribution of our statistic with that, okay? So there's some very clever and good reasons why this works. Okay, but basically we're going to actually do an independent sample and a fit over here, then we do it again, repeat exactly the same code. Okay, same code, different data. Okay, we do this, and of course they're independent. Okay, so we can do them in parallel. A grid search, same as the simulations, we just, hey, I'm trying to optimize a function and look across the different grid of parameters. We're just trying to find out which one has the smallest value or the largest value of a function, so we're just evaluating the function in parallel, and it doesn't actually matter. There are very good reasons why we don't want to do that, why it's a terrible way to optimize a function, okay? But if that's the way we're doing it, we can actually do this. Matrix multiplication, rows by columns, well, it doesn't matter. We can do the first row and the first column in different order, and we can do the third row and the fifth column in first or second, as long as we put them in the right place, and good. Inverting matrices, a little harder, but other people figured out how to do this. We're not going to do it, but there's an algorithm, and there's algorithms for a lot of things. Something as simple as this, we can parallelize. Okay, I said parallelize. Okay, there's two things. Parallelize is good. Parallelize. A lot of people drop out the last bit, and they make their code very slow. Okay, so but reading two CSV files, I'll show you an example later on. Where basically, I have a huge CSV file, I have another small one, and another little one, and another little one. Later on, I need both, okay? But I can easily just start reading this one in and keep going and doing all these other computations, then rendezvous back down here when both are finished. We know how to do this. We all know how to do that? Not in R, you don't. maybe you do, but R doesn't, because you can only do one thing at a time in R. It doesn't do anything in the background. So we got a slight problem. But it's clear that we could actually save time if it's clear if we can basically start here. Okay, start reading a CSV file, a.csv over here. This goes along. Then we start doing other things here, rendezvous over here, and now everything's done. All the time it took here, we were busy. All the time we took here is busy, but time, we've done twice as much in the same amount of time. Okay? And of course, we don't have to stop at one CSV, we can do lots of things. These are just background jobs, which hopefully you're familiar with from the shell. Who is familiar with doing background jobs in the shell, the Unix shell? Okay, two, not less than half, so it's good, because that's the obvious way to get parallelism. Okay, and we should use it. And then the other thing, which is, this is obvious too. If I have a huge long vector, how do I sum the vector? It's clear we can actually just break it up into chunks. Sum the chunks, and then sum the results of the chunks. Get the same answer. The order doesn't matter. But if I can actually, if I can do the operation on each chunk in parallel, we win. Okay. This is a good example actually where we can do this on a GPU, a graphical processing unit, which everyone has on their laptop. Okay. Better or worse, okay, but we have these very, very fast GPUs, which are very limited computers, or chips, but they're very, very, very fast, and lots of threads, lots of cores on them, so we can use certain things that to use. Okay. There's only one thing that's that you have to be careful about in parallel computing. Over here, okay, what we're actually going to do is this. I'm basically going to say, hey, go do something. You're busy. I'm going to be busy over here. This is going to be my master. This is the guy I'm typing commands at. This one goes off and does something over here. At the end of the day, I need the data set over here. Okay, it can't be over here. If this is in a trapped little R session over here, it's dead to me. Okay, I need to bring it back, and that's the problem. If this is 10 gigabytes big, I've got a problem. This is going to take me longer to transfer than if I just read it in here. Okay, everyone with me? So there's going to be a transfer cost for bringing the data back. Okay, and we want to minimize that. I'm going to send data over. Here it's going to be easy. I'm just saying, hey, here's a file to read. It's going to go off and read, and then I'm going to bring it back. In this case, it's only going to be bringing it back. If this turns out to be a 100 gigabyte file, and I only return back the sum of each column, and there's only 25,000 columns, that's tiny. Okay, then it's going to be very small. Now I've done a huge amount of processing outside. What I send back is very small, very fast. That's great. But if what I'm sending back is 100 gigabytes big, I probably want to actually read it in here and bring back the smaller part, which is less transmission cost. Okay, so sending data and bringing data back is going to be where you actually lose all the speed you get from doing things in parallel. Is that clear? It's pretty obvious. In general. The hard part is actually figuring out in your application what you should not be moving around. Okay, but basically, what we really kind of want to basically do is put the data somewhere and then send code to the data that's relevant to that sub-block of data. Okay, because data are the biggest things. Code is tiny. Okay, so that's what we really, really want to do. And what we're really trying to do is minimize the transfer time, but also maximize the computational time. If it takes 10 minutes to move this over here, that may be okay. If this step takes 2 days, okay, 10 minutes out of 2 days, no big deal. So it's all relative to how much the computational time is that you're saving. So if I'm doing 2 things and they take 2 days and the transmission time is very small, a portion of that, no big deal. Okay, very simple. And then there's this other funky thing which you may have come across with things like Hadoop and different distributed databases, whereas we actually send the data to different places, and then somebody, okay, that's the problem, somebody will actually then figure out where to send the code to. Okay, ideally you don't. Ideally the code just knows where to go, and the smart system so it figures out. But this is where we actually don't have all the data on all the machines, but we actually partition it up in such a way that we can exploit the fact that it's in different places and we send the code to the data. Okay, which is different. Okay, so what we're trying to do, just introduce you to some of the basic stuff. So as I was writing down, we're not going to be able to do that. And B, it's just too complicated. Then we'll focus on some of the elementary stuff in R, I say I'm happy to chat. We can as a group, we can chat about other things. But this is basically, so we'll stick to the simple stuff. But this is part of the problem. Okay, so most of you are sitting in front of a laptop. That laptop, I suspect, has at least 2 processors on it. Okay, it certainly has 2 cores. Okay, so what we actually have is we have a CPU, and oftentimes we have cores on a CPU. What's the difference between a core? And then we also have this thing called hyper-threading, okay, which gives us the illusion of even more. To some extent, it is an illusion. So when we ask the computer how many cores we have, sometimes it lies and tells us it has twice as many because they're hyper-threaded. You go like, yeah, but I can't really use them, and that's fine. But basically, many CPUs will actually have two or four cores, and oftentimes we'll actually have 2 CPUs. So this is a CPU and this is a core. And basically, you can think of these as being operating units, okay? They can actually do calculations, okay? One of the snags about all of this stuff, though, and this is something you really want to pay attention to, okay? Again, I'm talking totally generically, so it's all easy. The hard part is actually knowing what happens on your machine and in your computation. We have memory. So you've got a bunch of RAM on your laptop, okay? 16 gig, 8 gig, whatever it is. Okay, we've got different types of memory. We've got registers, which are really super fast. We've got L1 cache. We've got L2 cache. We've got regular RAM. We've got swap space, all of which are totally different. Okay, and orders of magnitude and speed difference between every single one of them. We have very few of these. We have more of these than this, but we have less of this than that because they're getting progressively slower and cheaper. Okay, bad news. We also have disks. Okay, and we also have network cards. Okay, network access. These are all shared by the CPU. Okay, by all the CPUs, by all the cores. So if this guy is doing a lot of work very cleverly, and this one is also working simultaneously, and they're both pulling data from the network or from the disk or from memory, they're competing with each other. So you're not getting the parallelism that you actually think you're getting. If they're not using any data, what the hell are you doing here? Okay, we're supposed to be doing data analysis. Okay, there are times when they're not, when you're just doing simulations and they're not pulling data, in which case they're basically independent of each other. They're not competing for resources. But that's going to kill us. This is going to kill us when we actually are reading files in parallel from the disk. Okay, which is shared. If there's 2 disks and the files happen to be on different disks, the disks can spin independently and we can access the thing, but then they still have to come back on what's called the bus. This is annoying. Okay, this is problematic. And then of course we also have these other beautiful things called GPUs. Sometimes we'll have 1 on your laptops, you may have 2, 3, or 4. Okay, but we still need to actually get memory data from this memory to this guy's memory, do the computations and send it back. So there's a lot of complexity to this. This is a wonderful thing. This is all shared memory multi-core that we're talking about, okay? Your laptop's here. I'll show you a machine soon, okay? Where the one we have upstairs from DSI, it's got 144 cores. It's got, I forget, a couple hundred megabytes of RAM. Hopefully we don't compete with ourselves. This is all good, but that's not what everyone has. Yeah.
Do virtual machines play the same analogy, or is that completely different?
Virtual machines have the same analogy. They're just virtual machines. You're sitting there. You've got an operating system running on a virtual machine. Okay, so and basically it thinks it has a CPU. It may think it has multiple CPUs. It's all life is good. It's got RAM. What's really annoying though is this is your real machine. This is your physical machine. Okay, this is the physical machine. It's actually got 4 CPUs. Let's say it's got 256 gig of RAM. It's got a whole lot of disks hanging off. It's got multiple network cards potentially, but you have multiple virtual machines. Okay, so now not only is this one competing, are the 4 CPUs competing, that the virtual CPUs are competing for these CPUs, the actual CPUs, they're competing with this guy as well. So when you actually spin up something in AWS, okay, Amazon Cloud, unless you have exclusive access to that machine, you're potentially actually competing with yourself and with other people. Okay, so you have, and that becomes unreliable because you can't, it's very uncertain as to what you actually are doing. Whereas at least in this case, if you manage to kill off the network, okay, close your laptop network connections and no one else can be on your machine, okay, you kill off your web browser because that's actually what's chewing up all your CPU cycles and RAM. Okay, but now that you have a dedicated machine, you can kind of reason about how much competition is going on. But then virtual machines are very complicated. So like even on this laptop, if I spin up a Linux box and my OS X box, you can see they're competing with each other. When one's heavily using the disk, the other one really doesn't have access to the disk. Okay, the different operating systems are sharing and so scheduling themselves somewhat fairly. Okay, but it's a real problem. Yep.
So each core can both read and write through this at the same time, or are there bottlenecks that arise?
Each core can try to read. Okay, basically, think about, we're going to have multiple processes running. Okay, you can do this with a thing called threads. But we'll just think about them as processes. They can do whatever they want, but they're going to have to ask. They're going to actually make a request to say, hey, disk, give me something, or I want to write to the disk. And the operating system actually queues up these requests and then figures out how to actually honor those requests. And it will actually have to serialize them. Okay, it may try to interleave them. So it might sort of say, look, you're trying to read a gigabyte of data. I'm going to give it to you in small chunks, and other people are going to actually get chunks coming in between, and that would be a good thing. So everyone feels responsive. Okay, but then we also have other tasks which are sort of say, we'll actually do things like saying, I get super user privileges, so mine gets higher priority. Okay, and everyone else goes way down, so I get a different scheduling algorithm.
So ultimately, they'll say if you're writing to this, then it basically has to be doing it one at a time, no matter how many cores you have.
Yes, for the actual writing, but what will actually happen is that the operating system will buffer stuff, and will actually figure out how to do this. This is actually one of the cases where you can, if you're lucky, under ideal circumstances, you can actually get super linear speed up in parallel, where you actually say, I'm writing over to the network or something like that. I have to wait, okay, but I'm going to go off and do something else while I'm waiting, because there's a natural latency involved. So I actually have time to eke out a few other commands in between, and the operating system can do this. This is actually what's going on a chip. I don't know. The chips are amazing things, okay? Chips are actually doing parallel computing on the chip themselves. They're actually speculatively branching when they come to an if statement. They do both sides of the if statement until it knows whether it's true or false, and then it throws the wrong one away, okay? Because it actually is utilizing more operations than it can, even though it's a complete waste of time. But it's not, because it's advancing the computation. But you're basically sliding extra commands in when you should be waiting, okay? So the other thing is that, and this is a very, very common situation. So all of you have laptops here. We could build a supercomputer of sorts here, okay? Okay, if you all allow us to log in to each other's machines, or allow me to log into every, so I can, from here, if I could log into all of your machines through SSH, I can set up a cluster, okay? And off we go. All I need to know is your IP addresses or whatever, the names of your machines, and I can log in. Now they're all going to be running independently, essentially. But clearly there's a problem here, isn't there? Okay, hopefully this is clear. If all the data lies on my laptop, I have to send it to all of you. Okay, so there's going to be downtime. But then if you're all prepared to sit here for a day or two, about 10 minutes to get the data across, and then we run simulations for hours and hours and hours and hours, then we win. Okay, so again, the relative time for transmission is small to the overall computational time, and that's good. So many of you will actually have access to a distributed memory. Okay, so multiple machines, that's what I mean by distributed memory. It's not the memory, the data are not in the same shared physical memory that we can access directly. So these are clustered computers. We have at least 11 of them lying around that are managed by a guy called Bill Broadley, who gave a talk here a couple of weeks ago. Okay, and he's the guy to talk to about this. There's other clusters around as well. Somebody had a hand up. Thank you.
Can you talk a little more about GPU?
We'll come back to that. Okay. Yeah. Okay. That's the fun part. Okay. That's the real Wild West. Okay. That's the the frontier. We're still discovering. Remind me to come back to that, please. Okay. And then so we have these clusters. How many of you use a distributed cluster? Okay. So let's say College of Biological Sciences has one, College of Ag and Environmental Sciences has one, the staff department has one, Math and Physical Sciences has one. So they tend to be shared because we pool money across different principal investigators, and then we you queue your jobs to run and all that sort of stuff, and they give you time. Okay, so this is all good. Of course, each of the machines in here has actually almost always has multiple cores with shared memory. Each machine is basically one of these. Okay, so now you've actually got a hybrid system. Okay, you've got in number 2, you've basically got multiple machines which are networked together. If we do it like the way I said, we do it my laptop to your laptops. Oh my God, we got Wi-Fi. Okay, so we got wireless communication, which is very slow. All the clusters are going to be connected through very, very fast. Ideally, the fastest network connections you can get, like NVIDIA and stuff like that. Okay, because now the data transmission is really important. Okay, but once you're on those machines, great. We can actually then do computations independently from the other machines, and there won't be this competition for resources, but there will be on that same machine. So we have this mix. How many of you know about threads? Few. Okay, so threads give you great control. These are actually running in the same process. They can actually share memory, and they can corrupt each other. They can start beating each other to death and accessing each other's data and writing in the wrong time. So we have to be very careful. This is really low-level stuff that we don't want to do. Okay, and you can't really do this in R. So you're lucky, you're better off, because basically you can write code that goes really, really fast and gives you exactly the wrong answer, okay? Unreliably, because the next time you run it, it'll give you a totally different answer. Next time you debug it, it will actually behave totally differently. So this is the ideal worst case scenario, okay? So we say about this. Then there's things like message passing interface. We also have Hadoop, which is a very common. How many of you know about Hadoop? Okay, how many of you have used Hadoop? Okay, a few, okay? Okay, so Hadoop is this big thing. It is totally generic. A lot of people were very annoyed when Hadoop became very popular because it's like, we've been doing this for years. Google puts a name on it, and all of a sudden it's a new invention. Okay, it's just a very, very simple idea of distributed computing. You can spin up an Amazon cluster and start install Hadoop in seconds and start doing interesting stuff. You can use it from R and all that stuff. Spark is an improvement over Hadoop that has various different things. And then we get into GPUs, which are fundamentally different. Okay, so the point about this is you can sort of see how different the actual hardware is and the software. The software is Hadoop is written in Java, Spark in Scala. You're sitting on top of these things. We have interfaces to lots of different languages. There is a different computational model here. Somebody has to manage the Hadoop cluster. Somebody actually has to manage the data. Okay, and then there's a wonderful book on Hadoop, which is the old book, and it was about 800 pages. Okay, there's a lot to it. Okay, and that's kind of more about using it rather than tuning it. And tuning is really, really important. This is a mess. And then there's all the distributed data stuff. Okay, so So that's the background. So if you think this is simple, that's great. I'm delighted for you. You get a nice naive view of the world, but just pick your poison, okay? And off you go, okay? If you happen to have a machine here with 2 CPUs, or 2 cores at least, you're good to go, okay? And why not? So this, for those of you a few of you said I've done this in the shell, these are shell commands, okay? Okay, and this is the obvious way to do parallel computing, and it works, okay? It really does work. Instead of being at the R prompt, you write a little R script. Most people actually have an R script, and they cut and paste the lines, and you use RStudio to highlight that and send it off. There's no need to, you just put it in a script. It's already in a script, it's in a file, and then you basically say, run this script, script 1, and this is, okay? And then now the big thing about this is, and this is not, I don't mean and then the next line is this, and then and the next line is this. This ampersand is very, very important in shell command, okay, which says, so this is a Unix shell command, but you can run on Windows, you can run on Mac, okay, as well, okay. R script, many of you have ever used the R script command. Good, thanks, wow, thanks. Okay, so R script just runs R, okay, but it just doesn't give you a prompt. It just says, the next argument on the shell command is is the file containing the R code to run, and I will run it. And then I will come back and finish. Okay, you will not get a prompt back until it finishes, and then it just does nothing. Okay, then it says, there you go, there's your prompt back in the usual R style. Okay, this is the shell, so there you go, I'm done.
What's the difference between using R script and R command, or CMD?
It's the whatever comes after that, the R command. What did you mean by R command after that?
I mean, there was an R command batch, or there was some older way.
Yeah, they're different versions of it. There's R command batch. I mean, okay, so this thing here, by the way, for those of you, when we run an R, when you just type R, so many of you will just click on the R Studio thing, that's fine. You don't know about any of this, okay, that's fine. But there's a wealth of things you can do. When you type R, you get the R prompt. When you type something like R command install for installing a package, or config for looking at configuration options, and a bunch of other commands, these are basically saying I want to use the R environment to run a specific R command, like git pull, git add. These are specific R commands, okay, not functions in R, but actually sort of commands in the installed version of R. And they just basically set up the entire R environment. R script is just one way around that, but it's very specific for running one script, okay? For what you give it the name of the shell script or the R script, and it runs that. Or we could, so they're basically the same thing for the most part. We can also do this R script -E for an expression, and then you actually type the actual R command in here, and it runs. Okay, so this is when we don't have a script, but we actually just we inline the expression on the command line. Okay, everyone happy? But our command is basically just setting everything up to actually work correctly. So these ampersands just basically put things in the background. I'm assuming that script 1 takes 5-10 minutes, an hour or so. So what I do is I basically just launch this, and the ampersand immediately gives me the shell prompt back. So I do it again. But now I don't want to give the same command. I don't want to repeat that. So I do script 2 and script 3. Now, basically, I've got the prompt back. I can go back to web browsing and all stuff. These things are running on my machine. If I have 3 CPUs available, they're running on independent CPUs. If they're all reading files, which they call it DR, so data from files, they're all competing for disk access. If I'm lucky, the first one reads the file really quickly, and then it starts doing some computations, okay? And then it never needs disk until it's trying to write the output out somewhere. And then this guy starts running, or it waits until this guy is finished reading, and then it starts running, okay? And then they go off and do their thing. So they're fighting for the disk access, but then most of their work is not actually contending with for resources. So that's good, okay? That's one way of doing it. If you didn't know about this, this is the other way of doing it. You just open multiple windows and type the commands in and wait. Okay, and then you keep going back and looking, see which one are finished. Okay, and you're sitting there and you're like, hang on a second, I have better things to do with my time. This is just a slightly more advanced way. Yeah.
So it's running on the CPUs, not the different cores.
You can think of the CPU. You can think of a CPU and a core as being one and the same. Okay, this is a computational unit. Okay, they're slightly funky differences and all that, but conceptually, that's what's running each instruction to the core. Okay, so yeah, and so basically we have all these cores. We typically say how many cores do I have? That's how many things I can run on.
Okay.
And by the way, you need one for the operating system. So don't give all the ones to your job and then go, now where's the operating system? And then you also, on your laptop, you also need Facebook. So keep one for Facebook. Music, so keep one for the music. Okay, and all of a sudden you got no course. So be careful. Good. There.
What happens if you're running this on a dual core machine? Like you're running 3 codes parallelly on a 2-core machine.
On a 2-core machine. So what's going to happen in that, you're already doing that. Okay. These 3 jobs, by the way, they look similar. These scripts could be totally different. Okay, but they're all our jobs. But we're already doing them. I could say go off and run Firefox. Go off and run Google Chrome. Now I've got 2 jobs. Okay. and then I fire up Safari. Now I've got 3 browsers running, and I'm using all 3 of them. Let's say there's only 2 CPUs. The operating system has 1 CPU. That leaves only 1 CPU really available for those 3 jobs. My mailer, my 3 browsers, everything. They're all just, the operating system is interleaving access to the CPU. Okay, it's a wonderful thing what the operating system is actually doing, that it actually looks so smooth. Okay, it's just saying, okay, you can have it for a second, you can have it for a millisecond, you can have it for 10 milliseconds, and as long as it does this in sufficiently fine-grained, you can't tell the difference, because you're just not fast enough to see the difference. So you're on my machine, when I run my web browsers, and the whole thing slows down because it's fighting for memory. Okay, so yeah, you can use it. But basically, they're all competing. They will all get scheduled. They just clearly will not get scheduled as fast if the fewer CPUs you have. Because somebody has to say, you can have it now, now you can have it. Whereas if they all have their own CPUs, the operating system doesn't bother getting in their way and doesn't schedule them. So if your operating system spends a lot of time scheduling them, you're losing time. You'd be better off running them serially. Okay, just give it a CPU. When it's finished, then give it the next command, because now there's no scheduling. That makes sense? So importantly, you can make code go slower by running it in parallel. And we do. So you think parallel compute. So let's just do this. I got 3 scripts. Let's now have 100 scripts. Well, I do not have 100 cores on this. So now I'm going to spend a lot more time actually scheduling them. I've said they should all be run in parallel, but I haven't given the operating system an instruction that says, actually, I want them to be done sequentially if you can't manage to do them in parallel. So this is where you have to actually come in and sort of say, I know something about my machine, okay? And I shouldn't be contending with this, okay? So you really can make it go slower. Yes?
I was going to ask about overclocking and 32-bit version of R and 64-bit version of R, if that would alleviate the data transmission issues you mentioned earlier?
Well, the overclocking is good. Overclocking is an interesting thing. What do we mean by overclocking? Who knows what overclocking is? Okay, overclocking is a way of destroying your CPU, breaking the warranty. Okay, and all sorts of interesting things. Yeah, you can overclock it. You can make it go. You can make it go run more instructions per second. Although it's, there is a really big problem. It is amazing. So maybe I'm just too old, but but I think it's still true. People who aggressively overclock basically get the wrong answer at least once in their life. Okay, and so if you're doing scientific computing or data analysis that matters, you want to be very careful, because you are running it beyond the specifications of the manufacturer, so there's no reliability. That's it. There's not any reliability in the first place for a chip, but that's fine. As for 64, 32-bit, that's second order consideration, considering the network traffic, the access. You are getting some benefit, you're also losing certain benefits in 64-bit. It's a wash. This is where we have to go back and profile, and you actually have to get into the details. Hopefully, what you're going to actually see is, look, this thing goes 4 times faster because I have 8 cores. Okay, you're not interested in milliseconds and down 1%. You're getting a factor of 4. Okay, and notice, by the way, I didn't say I have 8 cores, it's going 8 times as fast. If you get that, you're incredibly lucky. Okay, I have 8 cores, I only get a speed up of 4, a factor of 4. Is it really worth the 8 cores? That's up to you. Okay, but sometimes you will actually get. I'll throw 8 cores at it, I'll get a speed up of 2, 1.5. Is it worth it? Not clear. Okay, it is if there's no other use of the resources, but it's a problem. You're not necessarily getting full speed up. You're very rarely getting full speed up. Why aren't you getting full speed up? Talking with each other. Because they're talking to each other. Because the computation we did, which is read the CSV file and read this, we're still doing all that, but then we're also saying, oh, send it over here, create the R process, read this stuff back. We're actually doing extra work. And it can be big, okay, depending on what the actual extra work is. And even if this is all very small, they're still fighting for access to the memory and the disk and so forth. So the operating system is doing more work. So we've actually introduced a bunch of extra calculations. Now, the hope is that they're very small as a proportion of the overall time. Yeah? Everyone happy? So don't forget these. These are really, really simple ways of doing parallelism, okay? If you're familiar with the shell. And if you're not familiar with the shell, open multiple windows, okay? Okay? By the way, this is annoying. I'll see people do this where they have a script 1, script 2, script 3. The only difference between the scripts is the first one reads A.csv, the second one reads B.csv, the third one reads C, and so on. Okay, first of all, I've seen a lot of people do that. They'll cut and paste that script, or they just copy that script multiple times, and they'll go in and edit, they'll open the editor, A.csv. And it's so boring that they go A.csv, open the second file, B.csv, C.csv, E. Oh, I missed D. Or they'll, more to the point, they won't. They'll go D. Oh, did I do D? No, I'll do D again. Okay, so this is kind of nuts. What you can do with this is actually pass in command line arguments. Okay, that's the script, but it takes in extra inputs, which is the name of the file. And what we would actually do is we would write, and most people, many people haven't done this, we would write a for loop in our shell command. Okay, and if you don't know the syntax for that, you look it up. If you don't know how to write a for loop, that's good, because that means you're not using an R, which is good. It's not, but it's conceptually very simple. It's just syntactically, I have to sometimes remember which shell am I in, what's the actual syntax. But basically, you're going to sort of do a loop over all the files in a directory, and then call one script, and then pass in extra arguments. Okay. In addition to which, what you can actually do is you can, and we'll see this later on, but I'll just throw it out here. You could actually say our script, generic script 1 as the command line argument, stop, then 2, then 3, then 4, then 5. And it would just take that number and then go and look in R and go and look up and find the 5th file, the 6th file, the 7th file, and so on. So we can do a lot of we can move a lot of the computations out of the shell script and into the R script, just very simple things. Here's another really, really, really cheap and easy way to do parallel computing. Again, it assumes you have a lot of CPUs or enough CPUs, okay? And even if it doesn't, you can still, as I say, actually eke out some parallelism even when you only have one CPU. How many of you know about this? How many of you know about make? Okay, make is this weird thing that actually knows about all the dependencies. That's what's absolutely critical here in parallel computing. Before I can do the computation down here, I need to do all of these and this. There's a dependency here on all of the inputs from here. So great, somebody knows about that. We wrote that code. Okay, make will infer it with your help. Okay, but it will actually figure it out for you. And then it says, oh look, I need this, 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 and this, but they all can be done in parallel, and then I need to wait for them all to be finished, and then I can move on. Well, make -j and then a number here will tell it says to actually do this in parallel. Okay, so this is what I actually did. So if you so this is if you run R. I ran this on a machine with 144 cores. I gave it 16 cores. If I just say make. Well, this is building R from source. Make -j. If I just say make, it takes 6.5 minutes or 6.75 minutes. If I just say, I'll give you 16 cores, go ahead and try to use as many as you can. And it can't use all 16 at the same time because there's too many dependencies. But it cuts this down to 3 minutes. Okay, so about half. Okay, I like this because I like to build R frequently, which basically, and I don't want to wait 6 minutes. I'm trying one experiment and going, I'm not waiting 6 minutes to see if it worked. Okay, so this is very handy, and I can just throw cores out. Okay, not all the steps can be done in parallel, but what it is amazing when you watch this, it basically tries to compile all the C files in parallel. So it's just amazingly fast. You just see them shooting by. Okay, because they're basically not finished by the time it starts the next one. Yeah.
So the number you put in after -j is going to be the number of cores you should try to use.
Yeah, the number of technically it's going to be the number of parallel processes that it's going to use. That can be, I could put in 2,000 here. There's 144 cores. Now they'll just fight for it. They'll fight. Okay, so we tend to put in the number of cores that are available, but it can be more. And again, if one of them is actually going off, okay, so this again, this to me is the hardest part, and it's obvious, but just if one of those things goes off to download a file from the web, let it go, because that's on the network, okay? No one else is using the network. Well, it's already busy, but it's not using a CPU. to actually do anything. It's just literally waiting on the network connection to actually feed back stuff. So we're actually gaining something. There's now, so that's where we have an extra process that is actually more than the number of cores, then we're actually gaining some benefit. Okay, it's slightly unusual, but it's actually very common. But it's an unusual situation in the sense that that's because of network access. Okay, so some of them have to wait. Some of them are there's literally a dependency. I'm building all the C files. Okay, so like if we're in an R package, we'll compile all the .o files, but at the end we can wait till they're all finished before we put them together. So that guy can't be running parallel. He has to wait until that one's finished. Okay. I can't remember what's thing driving me nuts. It's very sensitive, and I can't remember if it's dropped off the edge or not. Doesn't scroll for some reason. There may be something. Okay, this is another technique that you can use. Okay, how many of you have ever seen this? It's an actual command on the Unix system called parallel. Okay, good. One person. Okay. So, okay. I wonder what it does. Okay, it just runs stuff in parallel. So here's an example. Okay, I have a bunch of bzipped files, CSV files. Okay, this is a simple example. It's actually, I do actually sometimes want to do. I want to count the number of records in all the CSV files. There's 22 files. This is the airline delay data that I often use. So what I can actually do is this. This is a shell command. I uncompress every single one of the BZ2 files. So I give one bunzip command, and I give it 22 files to unzip. And I tell it to unzip, not the individual files, but to put the contents out on the standard output. Okay? So it doesn't write them to disk. That saves me time. Okay? All I want to do is count the number of records. So this basically says one process processes 22 files in my case, and writes every single line to the standard output. And then on the other end of the pipe, we count the number of lines, and I get back one answer. Yeah?
The standard output.
Standard output. Okay, so this it's always fun when you leap into parallel computing and I haven't talked about shell programming. Okay, because we're moving a lot of things. Every process that you have, every process has 3 streams associated with it. Its input stream, where it reads you typing out or data coming into it. Okay, it has an output stream where it writes stuff to a console or a terminal or to file. Okay, and there's another one which is the standard error, which is actually where it writes its errors and any warnings that it has. Okay, you typically find the standard error and the standard output go to the same place. The screen you're looking at. Okay, but there are actually there are 2 separate screens. Okay, so bunzip this -c command basically says read this compressed file, read one line, and then write it out to the standard output. Okay, write it to the terminal. Okay, but this pipe says take that output and make it the input to WC, the word count. Okay, so we're not going to give this guy a file name. We're going to say the input comes from the output of that command, the previous command. Yeah, happy? So this is actually running it sequentially. It runs through 22 files, one after the other. Everyone happy? This is a parallel version of it. Here's the names of the 22 files. We pipe that into parallel. Here's the command we run for each of those. I tell it to use 22 cores. I say unzip that one file, whose name you will get as one element of this thing. And then, by the way, then I would get back 22 counts, counting the number of lines in each of the 22 files. Which wouldn't be good enough for me. I actually want to do the same computation. I want to actually add them all together. So now we use more shell script magic. I take the lines of text, which are the numbers, and I paste them all together with plus, and I hand them to this. What does BC stand for? Basic calculator. And oh my God, is it basic? Okay, so we actually basically, and what we're going to do here, it's going to take a string, which is a sum of text with a bunch of sums, and it does the computation. See what the difference is? This takes 357 seconds with this one, and this one takes 25 seconds. That to me is sufficient to actually, okay, I'm happy now. I can do this, takes me 30 seconds, great, I'm done. I don't wait for 3 minutes, so I'm an impatient person. Okay, everyone happy? Haven't got the R yet, have we? Okay. So we have actually covered R. These are your R scripts. That's the simplest way to actually run jobs in parallel. Okay, because what we're doing is we're running an entire script in parallel, and that's often what you actually want to do. Okay, it's just annoying because you actually have to either create these separate scripts, or you actually have to set up command line arguments to say what are the inputs to each of the generic script, which means you're programming in the shell, which is a little annoying. Okay, but you can even hide this in R if you really wanted to. How many of you have used this? How many of you were at Bill Broadley's talk? Okay, good. So how many of you have actually used Slurm? Okay, good. So Slurm is a way to actually, is a queuing mechanism. Here we actually, I say open up a shell and send a job to your laptop or something, okay? With Slurm, when you're actually on a distributed cluster with multiple machines and multiple people using it, okay, you have to be well behaved. You cannot just log in and start running a job, because A, how do you talk to the other nodes, the other distributed machines? But B, you also are going to get yelled at because, hey, everyone's got to play by the same rules. We've all got to put our jobs in a queue, and then somebody else schedules these for us and fairly. So like, for example, on some of these clusters that you will use on campus, some faculty members have actually put money in, okay? So they own a node. And when they say, I've got a job, their job will get scheduled within 1 minute, okay? Regardless of who else is there, okay? Because they own that node, so therefore they get a much higher priority. So you have to play the game properly. So Slurm is a good way of actually, it is a queuing mechanism, and you have to play by the rules of this game. I do actually have somewhere in this set of slides, I show you an R script and a Slurm shell script to actually run the jobs. Okay, it's very similar to this stuff that we were doing up here, but with parameters in here. Again, go back to the idea of, let me just say number 1, number 2, number 3, number 4 as command line arguments, and we look up which file to process. Okay, it's pretty easy. But again, this is very coarse-grained parallelism, where you're essentially running separate scripts in parallel, okay? Or the same script with different inputs in parallel. This is highly coarse-grained, okay? When you're actually running on a cluster, this is all great on your own laptop or on a single machine. There are some best practices which are just obvious. You should be using them anyway, but it's really important. If I've got multiple machines, okay, this is, again, hopefully all of this stuff is totally obvious, but it bears saying, if you've got multiple machines, okay, so machine number 1, machine number 2, okay, so we have lots of machines in the statistics department which we can actually run different things. This is great, okay, so I start my job here. This is going to be my master, and these are going to be workers. These are what we call them, okay. So I'm going to send jobs from here over to here. I'll do it through Slurm. I'll do it through in whatever way where we can do it through R as well. If basically I send over an R command over to here and to here, if they reference any data, that data better be on each machine. If they reference any R package to do their job, that R package better be installed on both machines, because even if it's installed over here, it's just not magically going to go over here. For example, this could be a Linux machine, and this could be an OS X machine, and this could be a Windows box. Okay, they can't share the same code. We're going to have to actually install the same packages on each of these machines. And we're also going to, you'll often send across a command that says source my functions.r. Okay, where's this file? It's over here. If it ain't over here, somebody's got to send it over. Okay, so the simplest way to do that is using version control. Okay, because you're using version control anyway, aren't you? Okay, so you know you've got Git running over here. You've got your code. It runs. You test it all here. Now you're ready to run in parallel. So now you Git clone over here or Git pull on over here. Now you've got them in the right places. You've got copies of up-to-date copies. The real annoying part is if you copy files from here to here, then you make a change over here. These guys didn't get it. Now you run these jobs for 2 hours, come back. That's odd. that seems wrong. Crap, I didn't update my code. So, you know, you need to make sure everything is in sync across all the machines. All the packages are installed. So version control is good. Our packages are really, really good because they basically say this is being installed. It's not like I didn't just git clone or git pull, okay, and forget to source that file or whatever it is. I actually install the package. I know what version it is. It is the correct version of the package. I have complete reproducibility and some verifiability. Somebody had a hand up. Yeah.
So on Slurm, when I log in using my login node and I install my packages on my R packages on the login node, I found that when I was submitting an R script for running it on the processing nodes, it never had any problem. I didn't need to install it separately.
Yep. Yep. You're lucky. Okay, if that's the case, so, but now we get into this again. This is why life is so complicated. It looks simple, and something. This is why I'm stressing a lot of these simple points, because there's actually a lot going on. If these guys are actually all sitting together and talking to a network file system, and that is where your data are all coming from, okay? So you have a home directory on each of these machines. And if that home directory is actually shared across all these machines, so it's the same file system. So if you make a change here, you automatically see it here and here. That's great. And is everyone happy with that? Because that really makes your life easy. Because now, if you install a package in your home directory, each of these guys sees it. Everyone happy? Everyone thinks this is going to make my life easier? There's two real problems here. First of all, if this is an OS X machine, they cannot have the same C code that compiles C code. They cannot be the same. So what you're going to get a great surprise. It sees the file, then it tries to load the shared library and goes, that's not the right format. So now you go. So now we actually need to actually start managing them ourselves on the same network file system. Oh, jeez, Louise. Okay, this gets messy. Okay, so but this does make your life ostensibly simpler. What's the other downside to this? So you have an R pack. You have a directory called R packages, let's say, and you install all the R packages. Now you don't have to install them across all these homogeneous machines. So if they're all running Linux, they can all use the same package. Okay, one time that's saved. Okay, we saved our time. Then they call source of some file. Well, the file is sitting here, so we don't have to synchronize this across. Life is good. Then we load up the data. So we've got a directory called data sitting under here. So each of these guys start loading up the data. Now we don't even have to tell it that it's in a different place. We don't have to send the data across, which might take us time. So we've saved a huge amount of time, haven't we?
I have a question.
Okay, well, let me finish this one first, okay, thank you. So basically, we didn't have to send the data to each of these machines. It had to ask for it, because this is not on each of these machines. This is a network file system. It's actually pulling across the network, which is notoriously slow. Okay, so we run this, and it starts reading this one data file here. Okay, or these 2 or 3 separate data files. It starts reading them. Then we get the wrong answer. Now we do it again. Okay, we fix our code, we do it again, and it has to read them again. Okay, so it's spending an awful lot of time doing data transmission. What was the bit we wanted to slow down? We wanted to avoid? Data transmission. Okay, so we've saved a lot of convenience. We've gained a lot of convenience, and we've lost a lot of bandwidth. Okay, so that's a downside to this. And it depends on the exact problem. But sometimes it's good, sometimes it's bad. Okay, so sometimes what we will actually do is, and you'll see this. I have 3 files, let's say. I'm going to put one on each of these machines. I'm going to move them across. I'm going to put them in the temp directory. And then I'm going to hit them so hard. I'm going to go and visit them hundreds of times so that I won't have to copy them across 100 times. Okay, I'm going to actually make them local because the disk speed is much, much faster than the network. Happy? Okay, so this is the downside. I mean, so it looks transparent. It's all magical until you go, why is it so slow? It's because the network. So, 1 second. Go.
So with regards to our package, because they're being maintained by individuals or independent of one another, if R gets updated and the packages don't, does that just mean that if your experiment relies on one specific version of R and that specific package, you can't update everything?
So there's lots of issues there, and one is that when you install packages, so typically what will happen is a lot of times your system administrator, which might be you, okay, will install R packages into a central place, and they will actually be local to the version of R. They'll actually go into that particular R installation. Then when you upgrade R from 3.3 to 3.4, okay, we basically have to go and install everything again. Okay. However, if you put them somewhere else, okay, R will see them in 3.3, and when you go to 3.4, R will still see them, and it will go, okay, that's okay. Now, when you go from R 2.0 to 3.0, or 3.0 to 4.0, R will go, you know, I can't use that anymore. And you have to install them all from scratch. And that happened recently, not with a minor with a version that didn't actually cross the major release number. Okay, so sometimes they're incompatible. Okay, but that's fine. So basically, you should always be reinstalling for that version of R. But on the flip side, if your code relies on R version 1.2 from 300 years ago, okay, and version 0.97 of some package, you can install that, and hopefully you have copies of that, and you can go and actually install that, and it will still run. Okay, ideally, but this is a whole version issue of actually if I need to go back and run. But if this is one of the problems here that I actually run into, if I have some centralized version of my packages and I run it across these machines, and this is running R 3.2, this is running R 3.3, and this is running R 3.4, they cannot all use the same version of the same package, the actual same installation of the package, so that I actually have to put them, I have to install them locally. Okay, and R helps you install them locally.
So do these problems go away if you use the cluster? Because like you tell a sysadmin, hey, I need this package, they'll all be local.
Most things go away if you actually tell a sysadmin to do what you want them to do.
Great.
The only problem is getting them to do. And this is an example of parallelism, actually. The sysadmin will do what you want him to do, as long as he or she has 100 other things ahead of the queue, in which case you're waiting for that thing. This is where it's helpful to be able to do stuff yourself. This is one of the reasons I want you to actually understand what's going on, because you can build R yourself. Okay, it's easy. You can install all the packages locally. Okay, you can basically you can replace the sysadmin except for with security access for the actual network. You can basically do everything you want but yourself, and it's very helpful because if the sysadmin says, you know what, it's Thanksgiving, I won't be around for the next 5 days, and then I'm going on a 2-week holiday, you're gone. Okay, 3 weeks, gone. It's nice to be autonomous. Okay, but yes, hopefully if everything is centrally installed, life is great, and they set up a network file system, or they actually install different software and different R packages on each of these machines, then it's all perfect. Okay, and if they can amortize that across multiple users, which they really can, then they're happy to do it. Yep.
So what if you have a big data set? Where would you put that data set, and how do you take these?
So if you have a big data set, again, this is the Wild West. Okay, how big is it? Does it fit on disk? Because if it doesn't fit on disk, then I need 2 disks. If it fits on 2 disks, well, that gives me an opportunity, because then I can actually put half of it on one disk and half of it on the other disk. Those disks would be on 2 different machines. They could be on different buses on the same machine. So it's giving, and I can also use this thing called RAID for redundant disks. And I can actually have them. I can have a copy, multiple copies of a file on different machines, and essentially what looks like a network file system. Okay, shared system, but basically this guy can see one copy and this guy can see a different copy, so they won't be contending with each other because they're on different disks. These are all good stuff. If it's really, really huge, and depending on what I'm doing, I might put it in a database. Okay, so this is where it really matters as to what you're actually trying to build and what your application is doing. I wish there was a simple answer. Okay, but it really depends on how big and how often you're accessing it. If it turns out that I'm going to run 100,000 jobs. Okay, pick a number. I'm gonna run a bunch of jobs, and they're going to visit that file 10 times each job. I would be much better off in copying that file over, so to each of these machines. Okay, I make a local copy on these because it takes me half an hour to transfer it to each machine. But now I'm going to run for a week. Okay, but if I'm going back and constantly querying the shared disk over here, that's a real problem because it's a huge file. But if I'm able to go in and actually just pull out tiny pieces of it, then maybe I'd be better off just pulling out those small pieces by going back and asking for a particular piece. This is why it's so complicated. Okay, this is where it gets hard because we get non-generic answers. Okay, everyone happy? Okay, this is R's parallel stuff. It's easy. Okay, use the shell. Okay, use slurm, use the shell to actually do stuff. Use the parallel command. Okay, to do stuff. But if you want to do this all in R, why do you want to do it in R? Because you're not running two scripts in parallel. You're running individual commands in parallel and getting the answer back and then moving on. Okay, we use R interactively a lot. It's because for data analysis, the whole point of R, the origin of the S language is literally, I kid you not, well before when I was in Bell Labs, where S was invented, they used to have programmers for the researchers. The researcher would say, I would like a plot of this. And the programmer would go off and do it and come back an hour later. There's the plot, and they would say, no, change the colors to this. Okay? You know, they fit a model and they go, well, I think it should be X squared, not X. And they go off an hour later. And that was kind of annoying for the programmers. It was also kind of annoying for the researchers because what we want is an immediate answer. I don't want to come back in an hour. Okay, but it took too long, so people built the S language. Okay, but the real point is, I don't know what I'm going to do next. I need to do some computation, look at the results, and then figure out what I'm going to do next. So that's where the script is not actually predefined. Okay, so now we're back into this world. There's a big difference between what we just talked about for the longest time. Okay, a lot of the same ideas, which about parallelism and contention and resources. But now we're basically saying, I want to actually run individual R commands in parallel as part of a bigger script, not to run the whole script in parallel. Then after that, what you end up with is now I've actually got the whole script, and pieces of it run in parallel. And that's a really bad idea. Because now I got four cores. And I go, now I've got this script, so I'm going to run that script on 4 cores. And each of those uses 8 cores. So now they're all contending with each other, okay? Because it seemed like a good idea because the scripts seem to be independent, but they're actually going to compete for multiple cores. So we have a little issue here about sort of this nesting of parallel commands, okay? Basically, there is a parallel package, and I say there's a whole lot of other stuff. I'll point you to the CRAN task view on high performance computing. There's a bunch of packages with GPUs, with Hadoop, Spark, all sorts of interesting different technologies. This is the one that's built into R. You can't not have it. When you have R, you've got the parallel package. Okay, this is super high level, super simple in some regards once you get the basic ideas. And life is good. We'll talk about GPUs more, but they become very, very specific. Okay, here do you load the parallel package? And by the way, this is now an oldish book, but it's nice and thin. I love thin books. I could read this. I can find time to read this. And it's only really one chapter, 2 chapters is useful. It's just called Parallel R. Okay, I mean the other ones are useful, but they're more. They talk about Hadoop and stuff, whereas you kind of just want to know what's going on. There's another book, which I have these listed down below. There's another book which doesn't cover the parallel package as much. It talks about other more exotic types. This is by Norm Matloff over in the CS department, called Parallel Computing for Data Science. Another interesting read. Okay, but for our purposes, this is the magic piece that we actually want. MCL apply. Okay. Again, ask lots and lots of questions. Hopefully you all know about lapply. If you don't, okay, you shouldn't be starting at the parallel stuff. You should start with the elementary stuff, okay? But lapply loops over a vector and applies a function element-wise to it and gets the answer back. It sure would be nice. That's the obvious thing we can parallelize, isn't it? I have a bunch of elements. I apply a function and put the answer back in the corresponding place in the vector. I don't care what order I do them. That's the beauty of lapply. It says I don't care what order you do them in. It's not a for loop where the ith iteration depends on the previous one. So life is good. So lapply is good. It says, well, come on, this is embarrassingly parallel. So MCLapply is the the one that causes us no embarrassment to use, and all you have to do is put MC in front of your lapply and it should work. What does MC lapply do? So, okay, I'll get there in a second. MC mapply is for mapply. Mapply is like lapply, except for it loops over 2 vectors and passes 2 arguments in, or maybe 3 vectors and passes 3 arguments to the function. So basically, it does it doesn't apply over a collection of vectors. And then the map is just another version of mapply. And pvec we'll talk about in a moment. Okay. Okay. Here is an example. Okay. Here's a bootstrap of a linear model. Okay. I fit a linear model. LM for linear model of my favorite data set, which is the MT cars, the motor trend cars data from the 1970s. Okay. Relevant as ever. Okay. So okay, we fit a model that looks like this, and I pull out the coefficients. And for some reason, I don't believe the normal theory. Okay, so I want to actually go and compute the bootstrap estimates of the coefficients. Okay, so what do? This is how you would do it in serially. I just repeat the same process over and over again. What is that? Basically, I sample the MT cars. Okay, the rows by. There should be a replace equals true here, by the way. I missed that. Okay, so MT car. I basically say. Take n, the number of rows, and give me sample those with replacement. Again, missing here. So it gives me, I have 1 through 32, and it gives me back 4, 9, 4. 4 is fine. With replacement equals true is exactly what I want in the bootstrap. Because I'm only going to get 32 rows back, not every row in the original data set will be there. That's fine. But this basically gives me a new data set. And then I pass it into LM again, and I get a different set of answers for each and every single time I do this. Everyone happy? That's the bootstrap. That's how simple the bootstrap is. Okay? This, I'm going to rewrite this because I want to use lapply. Replicate just basically says, it's the same thing as loop from 1 through 500 and do this thing, but don't bother using the iteration number. Okay? So basically what I do is I say lapply from 1 through 500. Here's a function that takes the iteration number and does nothing with it, and then just does that command. Everyone with me? Everyone happy? Anyone got any questions? Good. So it's just a simple lapply. I'm doing 2 things at one time here. Just focus on this guy here, okay? So lapply, which just says do it 500 times, give me the coefficients, and now we'll put them together. Now, what I'm actually going to do is this. Okay, I actually want this graph. That's the graph I want. Okay? Okay, what's this? This is the number of cores I'm using. This is the elapsed time for the entire bootstrap for that number of cores. So what I'm doing is, here's the number of cores. This is a bootstrap. Okay, this tells me how long it took to do that one bootstrap, and then I do it for each a number of cores from 1 through 8. First time I do it with just 1 core, which is just serial. 2 cores, 3 cores, 4 cores, up to 8 cores on this machine. This machine tells me it has 8 cores. Okay, okay, that's what I get. How many cores does my machine actually have? You can tell. Okay, and it could have actually been moved over to here. It depends what I was doing with my web browser at the time. Okay, if my web browser was fully active, I was occupying a core, so you have to be very careful. But basically, this is the serial time. It took about 0.49 seconds, okay? And then this here was what happened for each core. So clearly, it goes down, we're getting improvements. It's not a factor of 4, though, okay? It's only a factor of 2, okay? Because it's still competing for certain things, okay? There's also overhead, because what I'm actually doing is I'm actually firing up UR processes and sending the commands across and then getting answers back. That takes a little bit of time, okay? It takes very little time if I set up a UR process and had it run for an hour, that 1 second to set up the R process would be inconsequential in the overall time. So it depends on how long my computational task is. But this is what I get. This is so this is what's happening. We just basically said lapply, that was a single bootstrap serial. MC lapply said do them in parallel. Multi-core is what the MC stands for. Which everyone is that self-explanatory what multi-core means? No. because you think it is, but it's not. Okay, but there's some funky stuff going on here, which is actually very powerful. This is on the machine upstairs. I use 144, okay, 72 CPUs. 72 CPUs, 144 cores on this machine repeatedly. Apparently not. Okay, and what you're actually seeing is, look, got a huge speed up from going from 1 to 2 to 3 to 4 up to about 50, 45, 50. This is where the 72 cores come in. Now are the 72 CPUs. Now we're getting onto cores which do compete a little bit with each other. They're not quite independent. And look at the variability around here. Okay, now we're getting into weird scheduling issues and stuff like that. So if I ran it again, I'd get different answers, but there'd still be the inherent variability. But this is so going. But again, what have I got? I got a factor of 4 here, even when I'm at 40. So I'm not getting my bang for my buck, but hey, I don't care. It's not my buck. Okay. Okay. So it's already paid for. Nobody else was using it, so no big deal. Okay. Okay. So there is a function called detect cores. Okay. You can always find. You can ask R how many cores it thinks it has. You can go ahead and do that now. Just library of parallel detect cores parentheses, and it should give you back some number. On mine it says 8. I happen to know it's 4. Okay, again, get into hyper-threading and stuff, and people and operating systems a lot. But you can always figure this out. You shouldn't go above the number of cores that detect cores goes. I mean, you can under very, as I mentioned before, when you really know something about the fact that one of your jobs is going to go onto the network and spend a lot of time waiting, then you can actually do that. But you want to stick to this, okay? How does MCL apply works? Yeah.
There's an argument logical equals true or false to detect cores too.
In MCL apply?
In detect cores.
Oh yeah,
Logical
sure.
is
Yeah.
true or false.
Yeah, and so there's an enormous number of parameters and arguments you can use here to actually go and do stuff. But again, hopefully the cores work independently enough. Okay, they may not. Whether you actually want real hyper-threaded cores, non-cores or CPUs, this is something you have to play around with a little bit. It depends a little bit on your operating system, who else is running on the machine, and all sorts of stuff. Yeah.
Yeah, I tried to use MCL a while ago. It didn't work. Apparently it's because it's on Windows, and it actually says in the help, it says you can't use it because 14 is not available. What does that mean?
So it says not Windows, okay? Not
Yeah,
Windows.
not Windows.
Because we hate Windows users. We hate always have the pain of our life. Okay? The amount of work we've had to do to support Windows over the years is just like, oh god. Okay. I was just reading something totally unrelated yesterday. They were talking about operating systems, and they were just saying, operating systems. Windows is for business users, business executives. Linux is for programmers, software developers, and OS X was for graphical designers. I kind of like this. It's like the 12-star signs. Everyone fits into one. I have an OS X box. I am now a graphic designer. Okay? Not quite, but the fact is Windows does tend to be more on the business office side, if you will. So it's not ideal for scientific computing. Lots of people use it. That's fine. One of the problems is there's this thing called POSIX. You'll see POSIX mentioned in the help files. POSIX stands for Portable Operating System Interface, and then an X put on for fun. Okay, to make it pronounceable. The trouble is Windows is not a portable operating system. It doesn't adhere to a convention that is a standard. Okay, and as a result, we don't actually have access to this weird thing called fork that is available on Linux machines. And OS X boxes sit on top of Unix. Okay, so Unix and Linux say one of, for practical purposes in this conversation, they're the same thing. So we use this. There is a beautiful, beautiful thing we're taking advantage of. We'll talk about how to do this in not using MCL apply. So I'm going to show you how we can do clustering on any machine. Okay. There's another thing that this will not do. Not only will it not work on Windows, it will not work on 2 machines. It will only work on 1 machine. So if you've got 2 huge machines with infinite amount of RAM and infinite amount of CPUs, and you say MCL apply, it'll stay on the 1 machine. So if that's your laptop and you can see the other machines, and you go, oh, that's what I want to use. You're going to have to use something else. But what's going on here, why it's so useful, is because everyone has a couple of CPUs, so this is a very cheap way of doing things. Just add MC in front of L apply, and it just works. What's actually happening is, in the master, okay, this master guy over here, we say MCL apply. we tell it how many cores, or it finds out how many cores. Okay, okay. And what it actually does is, and this actually requires a little bit of thought. And I'm going to try to just outline this thing. So we're at the R prompt. Okay. So I basically say X is equal to read.csv file. Okay, CSV of some enormous big file. Okay, it's sitting here in X. And then I do mclapply, okay, of here's my, basically here's my, here's X and here's my function, okay? Now, what this is actually going to do, and I can pass in other arguments too, what this is actually going to do is immediately figure out how many cores there are, and it will construct, okay, it will construct this many workers, okay? So n core workers, okay? And the beautiful thing about this is these will be exact clones of the current R process, including having exactly the same search path. Any libraries you've loaded will now already be loaded in here. X will be available in here, okay? We don't have to send it across, it's already there. It's a piece of magic, okay? Where these are actually on the same machine as this guy, and they can see the same memory as the master. And as a result, we don't have any data transfer, okay? They go off and they do their computations and then they send the results back. That's the only data transfer we have. To do this piece of magic, we need this fork command, and that means you have to be on the same machines so they can see the same memory, and it also means that you actually have to have the fork command, and Windows doesn't provide it, so we're toast, okay? But for everyone, how many people use Windows here? Okay, so that's one of the drawbacks, okay? For this, we'll find a way around it, but that's what's going on. But do you see why it's so beautiful? Okay, I load this in once, and I know I don't actually have to have all my workers read this in again, or I don't have to send it across to my workers to actually be able to access that X. So when this function here starts, I shouldn't use X here, I'll use Y here, but if this function knows to refer to X, it's already there. The funky thing about this is, and again, just so you know, if this worker tries to change X, so it says X of 1, 1 equals 2, it will not change it in the master. It will immediately make a separate copy. But these two guys will still see the master's copy, okay? So this is really cutting down on the data transmission while still preserving the right computational model so that the calculations are correct. Okay, so it's kind of nice. Okay, but that's why it doesn't work on Windows. Okay, so if the master or a worker changes a shared object, they will get separate copies. This is very powerful, really super fast. This is one of the reasons why. Okay, just to cut to the chase here on this is mclapply. Where did we create the cluster? It did it for us, and it didn't give us an opportunity to hand in a previously constructed cluster. It's that cheap to actually spawn these things. So fork is so fast, okay, because it doesn't copy data. It just says, okay, there's another process that's running independently but has shared access to data. It's super, super fast. So what we do is we just create a cluster, do some computations, and then throw the cluster away. And then the next command can be another mclapply. Well, why didn't we keep the cluster around? Why do we have to start up these new R jobs? The answer is because it's so cheap. And also because if we do this sort of thing, because what I can actually do is this, Z is equal to this, and now I go W is equal to mclapply of something here with G, and this guy refers to Z. The next cluster that I can create will now have X and Z as shared objects, okay? So it's live, it's actually watching what we're doing. These guys go away, the workers go away. Now we create new workers, which are exact clones of the exact copy of the master when we call this latest mclapply, okay? So it's nice, really cheap, just doesn't work. Bummer. It works on everything except for Windows. Yep.
Following your
for the D and CLFI, the function is for changing the index.
So this is not changing. All my example here is basically we're looping over y, which is on. So we have a y in the master. So the master says, okay, you've got y. It's got 100 elements, and what it's going to, and then it applies f to each of these elements. Okay, and it's going to do it in parallel. But now I haven't gone through the details here, but just trying to get the point across that this function f can refer to x. So, okay, this is often what we do is we use a global variable in our function here. Normally global variables are bad, but in parallel world, they serve a purpose, okay? This function here will go and look at x, and each of these will have a copy of x. Now, as long as they just look at x and don't write to x, everything will be fine. The second they try to change x, then they'll have to make a copy of x. This is what R does anyway. When you pass x to a function, it doesn't make a copy, it just pretends to, and then when the second that function changes x, it will make a copy. So this is an extreme example because it's going across two versions of R. Is that okay?
Yeah, so it doesn't really help if you're trying to write the different x.
So this is where parallel computing often goes, which is this guy updates x, and this guy updates x, and this guy updates x. This is not the R model of doing anything, okay? Because that's not an L-apply. Because remember, the L-apply, they shouldn't be writing back into the same x, because then the order matters. Which one goes first? Now, we said in L-apply, the order doesn't matter. Now, in it, that's why we can use MC L-apply, because we're not even guaranteed they're going to go from the first, second, third, fourth. Now they're going to go in whatever order the operating system schedules them. So if these guys were actually writing back into X, oh, that's bad news. Because now they're if we did an L-apply, the last one would change X. Everybody else wouldn't change X necessarily, okay, depending on how we write it. What we tend to do in that model is this guy will do something and create a modified version of X. This guy will create a modified version of X. Or more to the point, it'll return back the pieces that needs to change. And then whoever picks them up at the end will put them back in the right place to X. Okay, this is what's called a functional programming language. We have no side effects. R is very good at this. It makes parallelism extremely easy. Okay, and so we don't have this function change X, because that leads to chaos. Okay, so that we always try to avoid changing global variables. Writing to global variables is bad. Global variables bad. A function modifying a global variable is really bad. Okay, and for parallelism, it is just okay. Okay, it just can't work. You have a question? No? Everyone happy? So that's MCL okay, except for the people on Windows. Everyone should be happy. That's all you need. Okay. Okay, it really is. Okay, and again, we don't care. No.
You know, your business executive world.
They only do one thing at a time. Okay, no, so basically it's all that's happening here. We're creating a clone, sending an R function and the arguments, okay? Okay, invokes the function in the clone, collects the answer, and puts them all back together again, okay? One of the funky things about MCLapply is what it's actually doing is it creates NC workers, sends each of them one element of X and the function, and says, go call that function, give me the answer back. When each of them, then it waits. And when they're all finished, it says, okay, round 2. So if I've got 12 elements in my X, in my vector X, and I got 4 cores, okay, it basically sends off 4 commands, waits for all of them to finish, and then goes into the second set of 4. So on the MCLapply, it depends on if you do this predetermined sketching.
Yeah.
So okay, okay, and then it goes off again, and then it goes again. Now, especially okay. So if you have an uneven number, that's fine. So you have fewer in the last box. Is there a better way to do this?
Yeah, it's a load balancing help like you're describing.
Okay, no, the one I'm describing that actually waits for each set to go. So that's not load balancing. Okay, so you go out, you say 4, you send a job off, and you wait for all of them to come back. Now imagine Okay, that one of the jobs, so I'm looping over 12 files. All of the files have 100 rows in them, except for one, which has 1,000,000 rows. Okay, so let's say that's the 4th file. So it says, okay, go read those files. Okay, the first 3 are quick. The last one takes for ages. Okay, but we don't start the next round over, the next 4 files, until everyone's finished. Okay, clearly I can do better than that, yes? I basically say, everyone go. When you're finished, when any of you are finished, let me know, and I will give you another job to do. Okay? And then we keep going. So if there's one computer, for example, this is where they're all running on the same computer. But generally, if I've got a very, very slow computer and a really, really fast computer, okay? This guy might be able to do one job in 10 minutes, and this guy can do one job in 1 minute. Well, I'm going to give this guy 10 jobs by the time this guy's finished one job. Or if the jobs are differentially computationally intensive, I want to make use of that. Okay, so that's when we actually use the arguments in MCL apply to actually say, do I predetermine the scheduling or do I do it dynamically? Okay, and the dynamic one basically says, I'll play this game. Okay, where I'm just going to wait for somebody to finish, and I'm going to give them the next task. If all the tasks are homogeneous and all the computers are homogeneous, it doesn't matter much. Okay, but if the tasks are differentially computationally intensive, or the actual workers are differentially capable, this may actually really matter. This is a thing called load balancing, and we'll see another example where it's actually in the name of the function. Okay. Okay, so you can actually go off and do this sort of thing. Okay, so there are 2 different mechanisms. There's even a 3rd mechanism which we'll actually do even better with. Okay, so just while we're at it, because I want you to understand this. Okay, here, if we do the following, what's happening here? Okay, so hopefully all of you know about this. So if we do something like lapply, here's my vector v. And here's my function f that I'm going to apply to this. And I'm going to pass in a and b and 10. These are extra arguments to the function f. Yes? Everyone happy? This is an enormous data frame, okay, of 2 gigabytes. This is a vector of length 2, and this is a scalar, okay? Now, I do MC lapply. What's the downside to this? So again, go back, think what MC lapply is doing. It creates this many workers, okay, 3 workers. It takes V, here's V, okay, with or without the load balancing, okay? Okay, either way, it sends off these 3 tasks. So V1, it does F of V1, F of V2, okay, and F of V3. Yeah, everyone happy? That's what it's going to start off with. Now, if it's load balancing, the first time one of any of these finishes, it gives the next one up, and it'll F of V4. But notice that I haven't passed in these arguments. It also has to pass across A, B, 10. Yeah, A, B, 10, A, B, 10. Life is good. Notice when we do this again, so now it gets to the 4th one. So suppose this guy finishes first. This guy is ready to go. Now it has F of V2, of V4, should I say, and it has to pass A, B, and 10 again. And if A is very, very, very large, so it's very, very bad. Okay? So this is actually where we might be better off saying, look, you got 3 of these guys. You take the first third, you take the next third, you take the next third. I'm going to send across A, B, and 10 once, and then while I'm over there, I'll do the loop on each of the sub-chunks here. Does that make sense? That's faster, is it? It reduces the transmission cost of A and B multiple times. But it doesn't do load balancing. Because if this machine is really, 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 really fast and could take care of 99% of the elements in one, faster than this guy can do one of them, then I lose that. So there's a trade-off here about load balancing, okay, and data transmission. See, I told you this wasn't easy. Okay, to actually make the code work super fast, you actually have to understand what's going on. But that's 3 different ways of scheduling exactly the same computations. One is do three computations, wait for all of them to finish, then send out 3 more and so forth. The load balancing version is send out 3, wait for anyone to respond with the result, then send out the next guy. And the other one is break it into 3 groups, have the workers do all the chunks, all the elements in each chunk, their own chunk, and then hand the results back. And that reduces transmission costs, but doesn't do load balancing. Trade-off. Yep.
So for this example, say the computer has a RAM of 2 gigs and A itself is 2 gigs. So what happens? Does it like exceed the memory, or is 2 gigs shared among the 24?
This is going back to my original picture of your sharing memory. So what's going to actually happen? Remember, we had registers L1, L2 cache, and then we had RAM and we had swap space. Basically, they're good. If everybody pulls in 2 gig of RAM, that's 6 gig of RAM for the 3 workers. That will go off to swap space. Eventually, it may run out of swap space. You can say, I really can't actually pretend I have that much memory. But basically, now everything's going to slow down a great deal. In which case, the operating system is going to do a lot of fighting to actually schedule these things, bringing them in and out, in and out, in and out. And you may actually really start losing valuable performance. And so you may be better off. This is a case where you may actually be slower running them in parallel. Even though you have 3 cores, they run slower than if you ran them sequentially. Okay, so the problem is this MCL apply and all this stuff makes it easy generically, but not for your particular problem. You actually have to try to understand some characteristics. The good news is we can measure this, okay, and we actually figure out what's going on, and we can you can adapt to it. But it is a real pain. You are contending. This is an example though where, hey, if I've got 3 machines, each with 2 gigabytes of RAM, each of them can handle the 2 gig problem, no problem by themselves. Now I don't want to be MCL apply. I want a cluster with 3 separate machines. Okay, and if you're lucky enough to have that, or if you spin up an AWS cloud machine and a cluster with 3 of those guys, life is good, because now they're independent. They're not fighting for each other. You're going to have to send the data across, but after that's done, then hopefully you can actually manage it in memory. But now you're sort of saying, the data transmission is not the problem, it's the memory that is the problem. So I'm going to change how I'm setting up my cluster. Okay? So how many cores to use? Okay, that's use detect cores. You play around with this. You figure out. There's no point if you're actually exceeding the amount of RAM. You're better off not using multiple cores. Okay, if you can run 2 jobs in parallel, then only use 2 cores. So it's all to do with the contention of the disk, the memory, the network, and all this sort of stuff. So basically, you're trying to make sure they don't compete with each other. Okay. Remember we had this example here. You ran off, get the a.csv. Okay, come back over here. You do all these commands here. Okay. I needed this essentially to be running in the background and then pull the answer back in later on. This is how you do it. Okay. Okay. There's a function called MC parallel. Here's the command that we actually run. That just goes in the background. We go off and we do other things. Okay. This is task 1, this is task 2, 3, 4, 5, 6, so on, okay? Then later on, we come back here. Now I know I need to go get the result. Hopefully it's all finished. Okay, hopefully I'll be busy over here. It's waiting for us, and that should be MC, that's the process, but these are just the generic commands. Basically what we're going to do now is we're going to say, you remember task 1? Go get the answer. Collect the results from task 1, and they'll be in A. Okay, this is a list with the result of the task 1 in the first element. Okay, so this is just a way of doing background jobs in R. Okay, and again, it's all running on the same machine with a clone of this R process working. So this is all that we've done here is this. It's basically said, go start running it. Go ahead, do this. Then go collect up the result. If this only takes me 1 second to do these things, and then this guy takes an hour, we'll just be waiting for a long time. But if this guy finishes before we get down to here, the results will be waiting for us when we go back and collect it up. Okay? So R takes care of actually handling all that for us. So it's very simple. We're avoiding passing stuff through files. So it's actually simple. And there's a whole lot of stuff you can do here. You can go back and say, are you finished yet? No, good. Then I'm going to keep going over on the right-hand side. Now I'll come back and ask you again later on, so we can figure out when the right time to actually do this is, okay? Okay, so let's go ahead. So PVEC is sitting there. We won't talk about PVEC, okay? So time out for the Windows people, okay? So there's a different set of functions that actually deal with distributed machines, okay? Or Windows machines, okay? So either one, okay? So, and this is super handy because we're actually working on it. Basically here, we have a function called make cluster, again in the parallel package. Make cluster, tell it the number of workers. If you're on Linux, OS X, it'll automatically do this forking business. However, okay, we can actually tell it which type of method to use, okay? I always have to throw this in. Critically, when you start a cluster, you are responsible for closing the cluster, stopping the cluster, or else somebody will get annoyed with you, okay, including you, okay? Okay, but here, this is a different way of actually starting them. This is more complicated than hopefully it'll happen for you. If, in the statistics department, we have several compute servers. I have the same login on every single machine. I have it all set up with SSH keys, so I can just log in without a password. There's no problem. I just say, hey, go and create 2 nodes on a machine called Hilbert and 3 nodes on a machine called Peter Hall. Okay, but in other cases, I have to say, you know, here's the name of the laptop. Here's the name of the machine. By the way, here's where R is installed on that machine because they're in different places. By the way, my login is not Duncan TL on this machine, but not there. Okay, I can configure all of these things. I basically describe each machine. I basically say, make a cluster in this way with 2 nodes on this machine, 3 nodes on this machine, and so forth. Now I've actually got these workers spread out across multiple machines. This Hilbert has got, let's say it's got 4 gig of RAM, so now I can run 2 jobs on that contain 2 gig of RAM, and they won't fight. They will work well. Okay, this one may have more, so I can run more. So I basically figure out how many nodes I can actually use. This is all going to use SSH. How many of you are not comfortable with SSH? Okay, so you want to know about SSH. It's a one-time deal where you basically sort of send your key over to the machine, so you don't have to log in with a password. And this is good, so you can remotely log in. It's a one-time deal. We can talk about that offline, but it's yet another trick that you have to actually learn. Okay. Now, the one problem with this is we are not forking, which means that the libraries, the search path, the packages that you loaded on the worker, they're on a different machine. They may not even be installed on the stupid machine. Okay, so you have to make sure that they're installed. You also have to actually load the libraries. Okay, so often what we want to do the first time is we fire up the cluster and we say, okay, let's get everybody up to speed. Let's load this library on each of them, or do the same command on all of them. Okay, and that's this command, which I seem to have repeated twice. Okay, cluster eval q. Okay. For those of you, this Q is for quote, eval is for, I want you to evaluate this R expression, okay? I have this in various different places, I can't remember where, okay? But basically what we're gonna do is we're gonna say cluster eval Q of the cluster. Notice what we did here. I made a cluster and I assigned it to some variable. I'm gonna call it CL for cluster. I'm gonna tell, I can have many of these clusters around the place if I want, but I basically now go and say, in this guy, I say cluster eval Q, to which cluster, CL, and then I just type, comma, library of whatever it is, library of maths, or library of some package that I want to make available. And then I also say, oh, by the way, x equals 1, I can assign x to 1 on every single machine. I can basically send one command, the same command across to every single machine, okay? The other thing I need to do is I need to export my data. Okay, oftentimes what we'll say, hey, you're all going to need a copy of X, and you're all going to need a copy of Y that I've already constructed. So we just send them across. We export to the cluster each of these variables, and they now become global variables on each worker. And now they're available for the computations that we can actually do. And now I can refer to those in a command like cluster eval Q. Okay, so if I send across the empty cars data, I could do the bootstrap. Okay, very, very easily because they all now have the empty cars data. Okay, and I can just send it across the command because it's exactly the same thing. There's also this thing that you can actually do that people don't seem to know is you can actually subset a cluster and actually only talk to particular nodes, which is very, 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 very useful, because now you can actually send particular tasks to particular nodes because you know that they have the data. So if I have two machines, Hilbert and P Hall, if Hilbert has one set of data and P Hall has the other set of data that I want to work on, I can actually basically have them, I can send commands to particular subsets of the nodes that I actually want. We're running out of time, so I'm going to say these notes are more for me. At the moment, there's a couple of other files that actually illustrate what's going on here. This is the idea, okay? MCL apply is basically going to fork on that machine, but it's really the same thing. Cluster eval queue, okay? And as we send stuff across for a generic cluster, that isn't one of these four guys. But then there is also these things called cluster apply and cluster apply LV and par apply, okay? So let me just do this one little thing, which is file. Let me just, actually I'll just do it here. So these are all that if you actually just go ahead and actually do an LS on the parallel package. We've gone through these functions, okay? The pvec, don't really worry too much about it. It can be handy, but you can figure it out. I'll tell you about it. Here we start creating and stopping a cluster. We have this cluster eval queue for sending it the same command to all workers, exporting variables, and then we can call a function. Okay, here's a function, here's a value. This is basically eval queue and cluster call. Eval queue just does a cluster call. So this is, you're giving the same command to every single worker, which is not that interesting. But cluster apply, cluster LB, and cluster map, the same thing, okay, are doing this here. Loop, the same thing as the MCL apply, loop over this vector, go and do these things in parallel. This does load balancing explicitly, okay? This one doesn't do load balancing, so you have a choice, okay? And then you have all of these functions, okay, which are just basically the power. These are just the different variations of apply, okay? What's the R and C stand for? Row and column. So if you have a matrix, this is all. So oftentimes we don't have matrices, so it's absolutely fine. Okay, that's really all there is to it. Basically, you can all we're basically going to do is this is the same thing as MCL apply. Okay, except for it works on a generic cluster. Okay, and off you go. Okay, I'm more than happy to take a whole lot of questions. That's all there is to the parallel stuff. Why do we? It's not very hard. The hard part is actually trying to figure out what contention you're going to have, what CPUs are going to fight with each other, who's going to get access to the disk, who's going to get access to memory, what is the right way to break my job. Hopefully, you've got everything. This is why we don't like people running for loops, because we can't tell if they can be done independently. Each iteration can be done independently. When you write it as an LPLY, you go, oh great, we know it can be parallelized, which means bingo, we're off to the races. We can just drop in MCL apply in place, and life is good. Okay, there's a couple. Basically that's all there really is to it, because it's that simple. That's all we need for this level, high-level parallel computing. This idea of actually going off and doing jobs in the background, very nice. There is this really funky thing that fortunately doesn't happen anymore, but you have to be aware of it. That's these guys down here. If you fire up enough processes and do random number generations, which you're intrinsically doing all the time, okay, a lot of the time, there's a real danger that if you do enough computations, the random numbers will not look random anymore. Okay? Random number generators basically have this cycle, and nobody ever hates the cycle. Nobody ever gets so it starts repeating itself in a way that you can just detect, unless you do enough of them. And if you do enough parallel computations, you can get yourself in so that it's where each of these processes actually starts looking like the other one, and that's really bad news. Okay, it's even worse if you actually think about the MCL apply. The old version of MCL apply used to do this. Okay, I think I have an example right here. I just want you to think about this momentarily. Yeah, this one. There's a package called Fortunes, and you just say, hey, give me a fortune, and it gives you a quote. It gives you some humorous little thing that happened on the RMA and for some snarky remark that somebody responded or whatever it is. Okay, so it's fine. Okay, so it basically has a big database, and it basically gives you it selects one for your adaptation. Okay, and then you move on. So people put this in in their R profile, so they get a fortune at the beginning of each session, okay? And then they call MCL apply. Just think about what actually happens here. It doesn't anymore, thank God. But think about what I said about what the MCL apply does. It creates a fork for each worker and makes all of the variables in your workspace available to each worker, an exact copy. That call to fortune actually generates a random fortune. So it actually has to pick a random number. So it sets the random seed in your workspace. Okay, and everyone gets a copy of that same random seed. And then you go off and do a simulation. And lo and behold, because you have just, as for the statisticians here, you're sitting there for your PhD, year 5, you're just finishing up. I've come up with the best estimator, lowest variance. I do a simulation across all my workers in parallel. Not only is it minimum variance, it's 0 variance. No variance at all across, because all of the workers have got exactly the same random seed, so they all get exactly the same random stream of values, okay, which is a train wreck, okay? But, okay, so that gets fixed because MCL apply now actually sets the seed for you. But there's also the whole lot of stuff that you have to be careful about, is that also they can actually start getting in sync with each other. And so there's a whole theory about random number generation in parallel that it's taken care of for you in the parallel package, but it's something you should be aware of. Other than that, there's no more parallel computing. It's all simple, unless you're using Hadoop, unless you're using GPUs, unless you're using Hadoop, GPUs, and R all together, which is perfectly fine. Okay, so there's a whole other world that you can actually get yourself into, threads and C++. This actually gets you a huge way. And if you actually just go back to what the timings I gave you, for just using the shell scripts, you can save a huge amount of time if you have enough cores lying around the place. So it should be hopefully very simple. If you have any questions after today, come chat with us, because we know. If you actually have some interesting code that you'd like to make parallel, if you think it's parallel but can't quite figure out how to make it parallel, not just dropping in MCL apply, but actually kind of reorganize the computations, come talk to myself and Clark, because we're kind of trying to figure out good examples of how you actually rewrite code automatically. Okay. Are there any questions now? Yeah.
Like more specific questions? Or?
Yeah.
Okay, I think we may have something similar. So let's say that we have, big data, not terabyte, but like a couple hundred gigabytes. Right?
Yeah.
It's a CSV file. I can't use like apply to run through it, right? Because I would have to first read in something that's like 300 gigs.
Yeah.
Let's say like a high partition cluster. So
yeah,
like 64 gigabytes.
Okay.
I do use a for loop to chunk it and perform functions on them, and I've been reading about 4 each.
Yeah.
In order to turn that easily into like a cluster chunking program. What are your thoughts on that?
That sounds good. It's a hard problem to some extent. So the idea is that you've got. So the other thing is, if you can split the file.
I've tried to do that in Unix, and it does this weird thing where like the last line has some pennies in it.
Yeah. So I mean, so you got a huge file.
Right. So I would like open a connection and do read table in chunks.
Yep. And this is absolutely fine. Okay. I mean that's the best you can do. If you have to, there's a trick.